We have two dates for the photoelectric effect. One was the discovery of the photoelectric effect by, who was that? Yeah, Hertz. And the other was the correct explanation of the photoelectric effect. That was 1905, and that was Einstein, yeah. Hertz used classical theory to explain the photoelectric effect. Photoelectric effect, by the way, says when light strikes a metal, an electron is sometimes ejected. That's the gist of it. There's lots of little subtleties to it, but in the end, that's the gist of the story. When light strikes a metal, sometimes an electron is ejected. Classical theory said this: light's a wave, purely a wave. The energy of the wave is related to its amplitude. In other words, how much of the wave you have. The brightness, the intensity of the light. Therefore, if you're not getting an electron ejected, there's insufficient energy. We need more energy. We need brighter light. That's what Hertz and his contemporaries predicted, but that didn't match the observations. So Hertz's classical theory explanation was wrong. It didn't explain what was observed. Enter Einstein in 1905 with his photon theory. Sometimes we call it quantum theory, photon or quantum theory, which said that energy is related to frequency. Light is a particle called a photon. The energy of a photon is equal to h times f, or hc over lambda. The energy of light is not related to the intensity. The energy of light is related to the type of light. Red light is lower energy than blue light. Ultraviolet is lower energy than X-rays because the frequency is lower. This explained the observations perfectly. An electron wasn't being ejected. Increase the intensity, nothing happened. Increase the frequency, something happened. Why? Well, because we increased the energy of the photon. Got it? So the accepted explanation for the photoelectric effect is the quantum explanation, or the photon explanation. It's Einstein's photon theory, which is that E is equal to hf or hc over lambda. Now, we have a couple more terms that go along with the photoelectric effect. We define the threshold frequency as, it was like that analogy we used yesterday, the day before, the pain threshold. The threshold frequency is, yep. Yeah, the pain threshold was the minimum amount of pain you need to experience to feel pain. The threshold frequency is the minimum frequency necessary to eject an electron. And that kind of goes along with lambda zero? Max, lambda max. That's the maximum wavelength. If we have a minimum frequency, we have a maximum wavelength. You got to be above a certain frequency. You got to be below a certain wavelength. There's another term that goes along with those two as well called the work function. That's the minimum energy necessary to eject an electron. Look, if energy is hf, then minimum energy is h times fo, minimum frequency. It's also equal to hc over lambda max. We're going to square off the first two parts of that because those are the parts that appear on my data sheet. The third part, we can figure that out on our own. Another term? We're going to use this today, not only in the questions that you had for homework last night, but in a graph that we're going to plot in a few minutes here. Stopping voltage or stopping potential. Once an electron has been ejected, sometimes you want to stop it. Why? Well, you'll see when we talk about this graph today, you'll see why you do want to stop an electron. But just say for now you want to stop an electron. It's been ejected, you want to stop it. How do you do that? Well, if you've got a car going, just kind of rolling along a level surface, you can stop that car by introducing a hill. The car starts going up the hill, it slows down, and stops. You can stop the electron by introducing a potential difference. If the potential difference is big enough, i.e. it's a value of V stop, then you will stop the electron that's already been ejected. Now, what kind of energy did the electron have when it was ejected, when it was released? As it moved away from the metal surface, what kind of energy did it have? Kinetic energy, right. So we're going to say, in this case, kinetic energy that the electron had, we'll call it EK max, becomes converted to potential energy, right? But not gravitational potential energy, electric potential energy, QV stop. Let's square that off, because that also appears on my data sheet. Now, I'm going to set that equal to 1/2 mv squared as well. Not going to square it, though, because it doesn't appear together on my data sheet. Finally, we have one more equation. It's the last thing we did yesterday. It comes from conservation of energy. EI equals EF. What is it that has the energy when this whole thing starts? When a photon strikes a metal and an electron's ejected, what is it that has the first energy? Tim? The electron or the photon? Yeah. The energy of that photon is HF. What is it that comes out of it? The electron. That would be kinetic energy, right? But we also lose a little bit of energy in the process. We call that the work function, the energy that is used up, or the minimum amount of energy that we need to eject an electron. I'm not going to square this one off because it's not on our data sheet. I'm going to highlight it, because although it's not on our data sheet, we're going to use it lots. Yep. It is joules per coulomb, or it is volts, either one. They're both the same thing. All right. The reason that this one that's highlighted here becomes so versatile, we use it so often, is because it has so many possible substitutions. HF, yeah, we can replace that with HC over lambda. EK max, we can replace that with 1/2 mv squared, or QV stop. W, yeah, we can replace that with HF0 or HC over lambda max. 6 different substitutions that we can do into this equation. So if you get some givens and you're not sure which equation you should try, probably going to be that highlighted one. That's the one that's the most versatile, has the most options with it. One more thing before we check our homework. I'm going to circle these 2 equations in red. Why am I drawing attention to those? What is it that stands out about those 2 equations versus everything else there? They're what? They're in the same equation, yes. You can see them in the same equation up here. Yep. Okay. E is equal to QV stop is on your formula sheet. E is equal to 1/2 mv squared is on your formula sheet, but in 2 different places. Yep. Yeah. Well, not just H, but everything needs to be in joules. If you're using one of these 2 equations, you must use joules. Here, I don't care, electron volts, joules, whatever you want. Here, joules, electron volts, whatever you want. Here, joules, electron volts, whatever you want. But as soon as you introduce 1/2 mv squared or QV stop, including up here, you've got to use joules. You cannot use electron volts at that point. You're going to see that rearing its head here in 1 or 2 of these worksheet questions you had for homework last night. Let's take a look at worksheet number 20 now, which was our homework. Question number 5. It says the work function of a particular metal is 3 electron volts. Will visible light of this frequency cause electrons to be emitted? The answer was yes, we said. But why is that the case? Well, there's 2 ways that we can tackle this. We'll call it the blue way and the green way. The blue way is to compare energies. So what I'm going to do here first is calculate. We know the work function is 3.00 eV. Let's calculate the energy of the photon using H times F. We're in EVs here for work function, so I might as well stick with EVs through the whole question. 4.14 times 10 to the negative 15 EV times S times the frequency of 8 times 10 to the 14 hertz. We do that, we get 3.31 EV. So this was our energy of our photon. This was our work function. Were electrons ejected? Yes, because the energy of our photon is greater than the work function. The energy that we have is greater than the energy that's required to eject an electron. Now there is another way to do it. And that is not to compare the energies, but rather to compare the frequencies. We have a frequency here of 8 times 10 to the 14 hertz. Let's calculate the threshold frequency. When we calculate the threshold frequency there, we end up getting 7.25 times 10 to the 14 hertz. Look, our frequency that we have here is greater than the threshold frequency. The frequency that we have is greater than the frequency that we need. So therefore, electrons would be ejected. You need to be bigger. You need to have an energy bigger than the work function. You need to have a frequency bigger than the threshold frequency. You need to have a wavelength less or smaller than lambda max. That's what you do in question number 6. Almost the same as question number 5, except you're trying to get lower than the wavelength, the threshold wavelength, as opposed to higher. Let's take a look at number 11 here. Calculate the max speed of a photoelectron emitted from a metal whose threshold frequency is 2 times 10 to the 15 when the metal is illuminated by a frequency of 2.5 times 10 to the 15. What do we got here? What do we got given to us? We've got a frequency of a photon of 2.5. And we've got a threshold frequency. This is what we have. This is what we need. We have 2.5. We need 2.0. We know that electrons will be ejected here, or at least one electron will be ejected because we have more than we need. Our frequency is bigger than the threshold frequency. What are we looking for? The max speed of an electron. Anybody have an equation for this? I'm not going to tell you what the answer is, which equation to use, but I'll give you a hint. You should think for 5 seconds or so. See if you can come up with one. Yeah? Then what is it? Yeah, you know what, even if you go to that one right away, like if it doesn't work, it doesn't work. Just try another one. You got a list of equations that you can try here. You get your data sheet on a test day, you should probably pencil in these things, right? Pencil in all these extra things that we wrote down. Then they're all in one place. When you get a question like this, go to that sheet. If you happen to notice right away that the givens match up with one of those equations, that's great. If they don't, just do what's highlighted in yellow there. Go straight to that. Because that's probably the one you're going to use if you can't figure out which equation to use right away. H, F, okay, we got that. EK max, we don't have that, but we can replace that with something. What are we going to replace EK max with? Mateo, don't know what EK max is? What do we replace it with? Yes, there is. Which one are you going to do? Yeah, 1/2 mv squared. Good. Anna, we don't know what W, the work function is. What do we replace it with? Sure you do. Let's look back at that list of equations here. We don't know what W is. We can replace it with HF0, or we can replace it with HC over lambda max. What are you going to replace it with? Good. Now we still have our numbers. Right? What do you want to use, 4.14 or 6.63 for H? 6.63? How come? It does have to be in joules. As soon as we introduced 1/2 mv squared, we've got to be in joules. The simple answer to that question, though, if I ask you 6.63 or 4.14, just say 6.63. Because that'll always work, right? As long as you're consistent through the problem, that'll always work. But Taylor, your reasoning was correct there. So let's use 6.63 times 10 to the negative 34 times the frequency. The mass is the mass of the electron. F0 is 2 times 10 to the 15. So let's get that number. Let's get that number. And then let's take it over by subtracting. And then let's times it by 2 to get rid of the half. And then let's divide it by 9.11 to get rid of a 9.11. And then we square root it. And when we do all that, we end up getting a value for V here, the maximum possible speed of this ejected electron, of 8.53 times 10 to the 5. Let's have you guys work on one question, number 13. Number 13. Let me just clarify something, though, in number 13, the wording of something. It says, when 230 nanometer light falls on a metal, the current through the photoelectric circuit is brought to 0 at a reverse voltage or a reverse potential of 1.64 volts. What are they telling me there? The current is brought to 0 with this potential. Austin, what is it? Yeah, if the current is brought to 0, that means we've stopped the electrons. So they're saying this is the stopping potential, 1.64 volts. You want to find the threshold frequency of the metal. Okay, go to town on that, guys. We got QV stop in here, so you got to use joules, right? Got to use joules. So let's go 6.63 times 10 to minus 34. Times 3 times 10 to the 8. 230 times 10 to the minus 9. Q is 1.6, right? The charge of an electron times 10 to the minus 19 times V stop. Plus, once again, 6.63. Seems like we usually use that anyways. Maybe we should just do it. Right? We say we can usually use whatever we want, but there's odd times when we have to use joules. Seems like we end up using joules more often than not, so maybe we should just always use it, all of us. F0, oh wait, we have V stop, don't we? We have V stop, it's 1.64. This is multiplied by F0. So what we're going to do now is calculate this, take this over by subtracting, then divide by 6.63, and get an answer. And when we do, F0 works out to be 9.09 times 10 to the 14 hertz. I want to describe for you now a relatively simple experiment that's used to determine some of the properties of a photoelectric surface, like a sodium surface or something, the threshold frequency, and so on. This experiment consists of an evacuated tube, which is just a glass tube with all the air sucked out of it. It has 2 electrodes. One is a collector, and one is the metal emitting surface. The collector you can see here is positive in this case because the battery or the power supply is hooked up like this with the positive side nearest that terminal. The negative side over here causes this electron emitting surface to become negative. Now there's an ammeter in here. Ammeters measure electric current. When there's no light shining on this, there is no electric current, therefore the ammeter reads 0. The reason there's no electric current is because there's not a complete circuit. There's a gap here in the evacuated tube between the collector and this electron emitting metal surface. But if we shine photons, let's say red light, red photons on this metal emitting surface, and those red photons have a frequency above the threshold frequency, they'll emit electrons. 3 photons will cause 3 electrons to be ejected. Those electrons get ejected like this. They end up getting attracted to this positive collector, and they end up going around a circuit, which causes this ammeter to no longer measure 0. It causes the ammeter to measure an electric current. I don't know what it is. I don't really care, to be honest, what it is. That's how this experiment is set up right now. Okay, we emit electrons, they go around a circuit, we get an electric current, we measure the electric current. Okay, the thrust of this experiment comes from the next thing we do, which is reverse the power supply. Question?
The electrons are from the metal, right?
Yes. Yes, the electrons are from the metal. It's not the battery that's causing these electrons to leave. It's the light that's causing these electrons to leave. Let's reverse this now. Now we have a power supply that looks like this, with a negative side right here and a positive side right here. That's going to cause this collector to become negative, and that's going to cause this thing over here, the electron emitting surface, to become positive. Now, if our photons still have a frequency above the threshold frequency, they'll still cause the electrons to be ejected. They'll be ejected, they'll go towards the collector. But because the collector is negative now, these electrons will slow down. And if the potential difference is big enough, they will stop. It's like a car going up a hill, right? If the height of the hill is big enough, what's going to happen to the car? It's going to stop. What we want to do is crank up this power supply until we stop the electrons. In other words, increase the electric potential difference until the electrons stop. How do we know when the electrons stop? We can't see them. Even if we look through a microscope, we can't see the electrons with our eyes. So how do we know when we've reached the stopping potential? How do we know when we crank this power supply up high enough to stop the electrons from going across to the collector? Ben? The ammeter reads 0. Okay? There was an electric current before. Now the ammeter is going to read 0 because we don't have electrons going around the circuit. So we can measure the frequency of the photon, and we can measure the potential difference in this power supply that was required to bring the ammeter reading down to 0, or required to stop the electrons. Now, if we increase the frequency, we see what the stopping potential is for the new frequency. It will be different. Then, this would be our data table. Then, we complete an analysis table. The analysis table has one different column, and that's EK max. What we want to do is convert V stop, the stopping potential, into kinetic energy. We're going to do that by saying EK is equal to QV stop. So now what we've got is a column for frequency and a column for EK max. Instead of F and V stop, it's F and EK. What do you think we're going to do with that? What do we always do with an analysis table? Graph it. We're going to graph it. If this is our data, our graph would look like this. Notice that this is a straight line. Like just about every graph we do is a straight line. We can analyze this graph. We know how to analyze any straight line graph. How do we start in any straight line graph? What's the first thing we do? We've done this on a number of labs now.
Read the title.
Well, what is the title? Look at the title. Notice the title is not photon frequency versus kinetic energy. It's kinetic energy versus frequency. It's always our y-axis versus our x-axis. So this is titled correct. Sometimes on your labs, you guys title it backwards. We've got the graph already plotted. We want to find out what the slope means, what the y-intercept means. What's the recipe for finding that out? Y equals mx plus b. It's a straight line graph. So let's say y is equal to mx plus b for this. And then we do what? Every single time. We do what? Yeah, get an equation. Y becomes equal to, well, what's on the y-axis here? That would be EK max, right? M is, what's M? Parker, what's M? Slope. So let's write down the word slope. X, what's on our x-axis? Nick, that would be what? Yeah, the frequency, so we'll just call it F. And B we can't get rid of here. Usually we can. The last couple times now we haven't been able to. The reason we can't this time is because if we extended that down, there would be a y-intercept. It doesn't go through the origin. There is a y-intercept. So we're just going to have to write that in. EK max is equal to the slope times F plus B. All right? Well, what's next? Find another equation. I'll give you 5 seconds to find another equation.
Oh, got it.
What is it?
That was like, not even a second. Highlighted one.
We're going to say HF, yeah, is equal to EK max plus W. That has the same two variables in it, right? But it's not in the same order, so we want to change the order of this a bit. Solve for EK. EK is equal to what? EK is equal to HF minus W. EK is equal to HF minus W. Now let's cross off things that appear in both. EK appears in both. F appears in both. What am I left with? Slope is equal to, Mateo? Yep. Slope times f, h times f. So the slope is equal to Planck's constant here. You might do an experiment like this to determine the value of Planck's constant. Get the slope of the graph. You might do an experiment like this to determine, what does B stand for? Y-intercept. What does it represent? Almost. Yes, negative W. The y-intercept represents the negative of the work function. So let's say that on this graph, let's say you had a y-intercept of, let's say, negative 10. Just picking a number out of a hat here, negative 10. That would mean the work function would be negative 10, or the work function would be 10. So get your slope, Planck's constant. Get your y-intercept, it's the work function. Sometimes you get your y-intercept just by reading the graph. Sometimes you plug it into your calculator. Remember using that stat function in your calculator? That will give you the slope and the y-intercept. Now there is one more thing that we can get from this. This is not quite as formulaic or as recipe as the other two things are. What do you think the x-intercept is? Like, think about this. Don't just guess. Think about it. It is the threshold frequency, yes. Think about below this frequency. At this frequency, the kinetic energy is negative. Well, you can't really have a negative kinetic energy. Negative kinetic energy, negative kinetic energy, negative kinetic energy. This is the first frequency at which electrons begin to have kinetic energy. This is the first frequency at which electrons begin to be ejected. That's the threshold frequency. So we've got three things here. Planck's constant, the work function, and the slope. They all relate to one another by this equation. Technically, with this graph, you don't need this equation because you have all of these things from the graph, right? But here's a little trick sometimes.
Negative b would be double over slope, which is h.
Yes. Yeah, it's exactly the same thing, yes. But sometimes you might notice here, since you're able to find all three variables, sometimes maybe you find two variables. Maybe you punch the numbers into your calculator, you get the slope and the y-intercept. You got the slope and the y-intercept? All right, you don't need to find the x-intercept anymore because you can just use the equation. If you have two parts of the equation, use the equation to find the third. Yeah, the other thing you can do here is, once you've got all three of these things from this graph, use the equation to check your work, right? If you get the numbers from the graph for the slope of the y-intercept and the x-intercept, and W equals h times f0, then you must have been right. Does that make sense?